Every detail in this story comes from real scientific research and observation. There is a moon you have never heard anyone describe. It is smaller than the state of Arizona. It is so cold that the surface temperature hovers around -201 degrees Celsius. And yet, beneath its skin, there is an ocean. Not a frozen one, a liquid one. Right now, as you are breathing, a sea of salt water is moving in the dark beneath an ice shell nearly 30 kilometers thick, warmed not by a sun it can barely see, but by the gravitational pull of a planet so massive it flexes the rock itself. And it has been doing this for hundreds of millions of years. There are cracks in the ice, 4 of them parallel, each one roughly 130 kilometers long, each one glowing warmer than everything around it by more than 100 degrees. From those cracks, water is launching itself into space. Not dripping, not leaking, launching at 1,400 meters per second. The plume climbs hundreds of kilometers above the surface, freezes, and falls back as snow. And inside that plume, captured by a spacecraft moving at 21 kilometers per second, there were organic molecules. Complex ones. The kind that on Earth you only find in one context. Life? We do not know if anything is alive down there. But we know the conditions are right. We know there is liquid water. We know there is chemical energy. We know there is heat. We know there are the building blocks. Everything that life needs on a moon the size of a city, spinning silently around a ringed planet 886 million miles from the sun. Tonight, you are going there, not to find the answer, but to be present with the question. This is Quiet Science at Bedtime. If this is your kind of story, a subscribe means everything right now. Every detail you are about to hear is based on real measurements, real missions, and real data gathered across decades of planetary science. Just relax and feel free to let this play as you drift off to sleep. Now, let us begin. Saturn is the 6th planet from the Sun. It orbits at an average distance of approximately 1.4 billion kilometers from the Sun, roughly 9.5 times the distance between Earth and the Sun. At that distance, sunlight arrives at about 1% of the intensity you feel on a clear afternoon on Earth. Saturn has 83 confirmed moons. Most of them are small, irregular, unremarkable, captured asteroids and fragments from ancient collisions, locked in orbits they have held for billions of years. But one of them is different. Enceladus, designated S2 Enceladus, was first observed by the British astronomer William Herschel on August 28, 1789. He saw a point of light. He noted its position. He recorded it. And then for nearly 200 years, it was just that, a point of light. It was not until the Voyager 2 flyby in 1981 that anyone saw its surface, and what the spacecraft returned was strange. Parts of the surface were ancient, heavily cratered, consistent with 4 billion years of bombardment. But other parts were almost completely smooth. No craters. Fresh. As if something had resurfaced them recently. In geological terms, recently can mean within the last 100 million years. The scientists noted it, filed it, and moved on. It would take another 20 years and a different spacecraft to understand what they had almost seen. Tonight, you are crossing the distance between here and there. You are moving away from Earth now. Behind you, the planet shrinks, blue and white at first, then blue, then a blue point, then nothing. The sun behind you is still bright, still warm on the instruments of the craft carrying you outward. You are moving at approximately 30 kilometers per second relative to the sun, a speed that would cross the continental United States in under 3 minutes. But the solar system is vast. Even at this speed, it takes years to reach the outer planets. You are not impatient. There is nothing out here to rush toward. There is only the dark and the slow, steady motion of one small craft through an ocean of nothing. Ahead of you, Jupiter appears first, not as a planet, but as a brightening in a particular direction. You pass it without stopping. Its gravity bends your path slightly, adding speed through a gravitational slingshot maneuver that costs no fuel. This is how the Cassini spacecraft traveled to Saturn, launched in October 1997, using gravitational assists from Venus twice, Earth once, and Jupiter once, before arriving at Saturn in July 2004. 13 years of operational mission. 360 orbits around Saturn, 23 close flybys of Enceladus alone. But you are not there yet. You are still in the dark between Jupiter and Saturn, watching the sun shrink behind you. At this distance, the sun is no longer warm. It is simply bright, a point of intense light surrounded by the same black that surrounds everything else out here. The temperature of your environment, were you outside the craft, would approach negative 270 degrees Celsius, just 3 degrees above absolute zero, the theoretical minimum temperature in the universe. Nothing moves out here except you. No wind, no current, no weather. Just the faint pressure of solar photons against the hull, a force so small it is measured in micropascals, a unit almost too small to mean anything in human experience. And then, slowly, very slowly, something begins to resolve ahead. A cream-colored disk, wider than you expected, and around it, a ring. Saturn. You have been moving toward this moment for years of fictional transit, and now the planet fills more and more of the forward view, until it is undeniable, a world so large that more than 700 Earths could fit inside its volume. Its diameter at the equator is approximately 116,000 kilometers. Its rings extend outward to nearly 280,000 kilometers from the planet's center, yet in most places they are less than a kilometer thick, a structure so wide and so flat that if you scaled it to the size of a sheet of paper, the paper would be thinner than the rings. You slow as you approach. The craft performs its orbital insertion, a long engine burn that bleeds off speed, allowing Saturn's gravity to capture you. And now you are in orbit. And now you can begin to look. The moons are everywhere. Most are small, tumbling, irregular bodies that look like potatoes or broken stones. But there, tracking along a faint bluish arc in the outer B-ring region, a ring called the E-ring, wide and diffuse and faintly luminescent, is a small white sphere. Enceladus. Even from here, it is startlingly bright. You have seen other moons by now, Mimas, Tethys, Dione, and they are all pale, as most icy moons are. But Enceladus is different. It does not reflect some of the light. It reflects nearly all of it. Its albedo, the scientific measure of reflectivity, is approximately 0.99. That means it reflects 99% of the sunlight that strikes it. For comparison, fresh snow on Earth reflects between 80 and 90%. The surface of our moon reflects about 12%. Enceladus is the most reflective body in the solar system, and that tells you something before you even get close. That surface is fresh, not ancient, not dusty, not weathered by billions of years of micrometeorite impacts, which slowly darken every exposed surface in the solar system. Something is renewing it. Something is covering it continuously with new material. You are going to find out what. You adjust your orbit to bring you closer. The craft descends, not in a straight line, but in a long curving approach that follows the gravitational geometry between your velocity and Saturn's pull. And as you descend, Enceladus grows. It takes shape. At first, it is a disk, then a globe, then a world, 504 kilometers across, small enough that you could walk around its equator, in theory, in about 2 months of continuous walking. Small enough that its gravity is only about 1/100th of Earth's. If you stood on its surface and jumped, a modest jump, just enough to lift you a meter off the ground on Earth, you would rise slowly, float for a moment, and land again. A harder jump might send you drifting into a low arc before settling back. And a very hard jump, a running leap, could, theoretically, launch you into a slow, lazy orbit just above the surface. But you are not thinking about jumping. You are watching the surface resolve below you. The northern hemisphere comes into focus first, and what you see there is old. There are craters, hundreds of them, of varying sizes, ranging from small depressions less than a kilometer across to large impact basins many kilometers in diameter. This is what every icy moon in the outer solar system looks like. This is what 4 billion years of being hit by things looks like. The cratering rate in the outer solar system is lower than in the inner solar system, but it is never zero, and over billions of years the accumulation is significant. Each crater represents a collision, a rock, an ice fragment, a piece of some ancient shattered body, arriving at several kilometers per second and excavating a depression that has persisted ever since. The northern terrain is ancient. Scientists estimate it to be approximately 4 billion years old, formed in the early solar system and preserved since then by the extreme cold. But as your orbit carries you southward, something changes. The craters become fewer. The terrain becomes smoother, and then the craters disappear entirely. The southern hemisphere of Enceladus is one of the youngest surfaces in the solar system. Where the north is ancient and pockmarked, the south is almost perfectly smooth, a vast plain of ice with no significant cratering, suggesting that it has been resurfaced within the last 100 million years. Perhaps more recently, perhaps much more recently, the south pole of Enceladus looks like it was repaved. You have crossed the equator now, descending toward that smooth southern terrain, and the surface below you is eerily clean. White, unbroken. But then, at around 60 to 90 degrees south latitude, something interrupts the smoothness. Ridges. Long, sinuous ridges that cross the terrain in broad arcs, like wrinkles in skin. And then converging toward the South Pole itself, something more dramatic. 4 long, straight lines. Parallel. Evenly spaced. Dark against the white surface. Even from orbit, they look like something has been cut. Like someone has drawn 4 lines across the face of the moon with a blade. They are not random. They are not the result of random impacts or chaotic geological processes. They are too regular, too orderly, too deliberate, though nothing deliberate made them. They are the result of physics, of stress and pressure in the slow accumulation of forces that eventually exceed what the ice can bear. You are going to land near them. Your descent begins. The craft adjusts its attitude, rotating to face the heat shield forward, though in this thin and frozen environment, there is no atmosphere to cause the fiery re-entry that returning spacecraft experience above Earth. Here, the descent is quiet. Cold? You fire thrusters to reduce speed, and the surface rises to meet you. The plane of the southern hemisphere fills your forward view now. You can see the texture of the ice, not perfectly smooth up close, but covered in small ridges and hummocks, ice that has cracked and refrozen many times over its history, leaving a surface that looks, in places, like crumpled aluminum foil. The 4 great lines are to your south and below. You can see one of them from here, a dark scar across the white surface, wider than it appeared from orbit, cutting through everything around it with a clean, decisive clarity. You land. The thrusters cut out, and there is silence. Not the comfortable silence of a quiet room. A different kind of silence, total, absolute, the silence of a place where there is no medium for sound to travel, no air, no atmosphere, no wind, no weather, nothing but vacuum and ice, and the faint gravity of a world that is mostly empty space. The temperature at your landing site is negative 198 degrees Celsius. That is cold enough that nitrogen, the gas that makes up 78% of Earth's atmosphere, would liquefy. Cold enough that carbon dioxide, the dry ice that your experiments produced at school, would freeze solid from its already frozen form into something harder and more dense. Cold enough that most of what you know as gas exists here as rock. But not everything. You're sitting still now. You allow a moment to simply exist here, on the surface of a moon that almost no one thinks about, orbiting a planet that most people have only seen in photographs, in a solar system so vast that the nearest star is still 4 light years away. You are very far from home. The sun from here appears as an unusually bright star. Not a disk. Not the warm yellow circle you know from Earth. A point. A very bright point, providing enough light to see by, faintly, dimly, in the way that a full moon on Earth provides just enough light to read, but not enough warmth to matter. Sunlight at this distance carries approximately 1% of the energy it carries at Earth's surface. 1%? Not enough to warm you. Not enough to drive weather. Not enough to evaporate ice. And yet, despite this, there is liquid water beneath you. Not because of the sun, because of what you are orbiting. Saturn is pulling at you. Even here on the surface of one of its moons, you feel nothing. The tidal forces are far too subtle for any human sense to detect. But in the rock and ice beneath your feet, in the silicate core that sits at the center of this small world, those forces are doing real work. Enceladus orbits Saturn at a distance of approximately 238,000 kilometers, measured from the center of Saturn to the center of Enceladus. For comparison, our moon orbits Earth at an average distance of about 384,000 kilometers. Enceladus is much closer to its parent planet proportionally than our moon is to Earth. And Saturn is much more massive than Earth. Saturn's mass is approximately 5.7 times 10 to the 26th kilograms, 95 times the mass of Earth. At the distance Enceladus orbits, that mass creates a gravitational gradient, a difference in gravitational pull between the side of Enceladus facing Saturn and the side facing away. That difference is the tidal force. The same force that causes Earth's oceans to bulge toward and away from the moon, creating tides. But on Enceladus, the effect is much greater because the moon is rigid, solid rock and ice, and so the tidal force does not cause water to slosh. It causes the rock itself to flex. Slightly. A few meters of deformation per orbital cycle. And that flexing creates friction. And friction creates heat. This is called tidal heating, and it is the reason Enceladus is not frozen solid, despite receiving only 1% of Earth's sunlight. The orbital period of Enceladus, one full orbit around Saturn, is approximately 32 hours and 53 minutes. Every 32 hours, the tidal stress cycles through Enceladus's interior, compressing and relaxing the rock, generating heat deep inside. There is also a resonance effect. Enceladus orbits Saturn in a 1-2 orbital resonance with another moon called Dione. For every one orbit Enceladus completes, Dione completes exactly half an orbit. This keeps Enceladus's orbit slightly elliptical, preventing it from settling into the circular orbit that would reduce tidal heating. The resonance with Dione keeps the heat on. The heat stays. The rock stays warm. And somewhere beneath you, at depths that will take you hours more to reach, that warmth is doing something extraordinary. You are not moving yet. You are still sitting on the surface, looking at the horizon, which is close here on a moon this small. The horizon of Enceladus is only about 400 meters away, compared to Earth's horizon of about 5 kilometers at sea level. The curvature of this small world pulls the horizon toward you, makes the world feel intimate and close, like standing on a very small hill. Beyond the horizon to the south, you cannot see the 4 great cracks, but you know they are there. You have seen them from orbit. You will walk toward them now. You rise from where you have been sitting. The motion is slow in this gravity. Your mass is the same as it always was, but your weight here, on the surface of Enceladus, is about 1% of what you weigh on Earth. Every movement takes adjustment. Every step lands softly, and the recoil carries you slightly upward before gravity brings you back. You are walking across the southern plain of Enceladus, heading toward the South Pole. The ice beneath you is hard, not the soft granular snow of an Earth winter, but compacted ancient ice formed under the relentless cold of a world that has never been warmer than -200 degrees. It crunches faintly under your steps, or rather, you imagine it would if there were any air to carry the sound. There is no sound here. Your footfalls are completely silent. The surface is almost perfectly flat in this region. The resurfacing events that smoothed the southern hemisphere also leveled it, filling in any significant topography with new material. But ahead, you begin to see the first subtle signs that the terrain is changing. Low ridges, gentle undulations. The ice here is not ancient. It was laid down relatively recently in geological terms, and it has its own topography, its own character. The ridges run roughly parallel to the great cracks you are approaching. They are stress fractures, places where the ice pulled apart or buckled under the same tidal forces that keep the ocean liquid, cycling with every orbit, every pass around Saturn. You keep walking. The temperature here is the same unbroken cold you landed into. But ahead, something is different. There is a faint haze above the horizon. Not fog. There is no atmosphere thick enough for fog. But something. A slight brightening above the horizon, as if something is catching the dim sunlight at a different angle. You are seeing it before you understand it. You are seeing the top of the plume. You are close now. The first crack appears without drama. One moment you are walking across a smooth white plain, and then there is an edge, a sharp drop into a narrow valley that cuts across your path from horizon to horizon. You stop at the edge. You look down. The walls of the fracture descend steeply, dropping perhaps 500 meters before they are lost in shadow. The crack itself is narrow at the surface, perhaps a few dozen meters wide where you stand, but you can see from the geometry of the walls that it widens deeper down. The walls are layered, different shades of blue and white, marking different episodes of ice deposition, different moments in the history of this fracture. And the walls are warm. Warm is a relative term here. Everything you have been standing on is -198 degrees Celsius. But the wall of this fracture, where it faces the interior of the crack, reads significantly warmer on your instruments. Still cold by any Earth standard, -120 degrees Celsius near the surface of the wall, and warming further as you look deeper. But in the context of this world, this fracture is blazing. This is one of the tiger stripes. And tomorrow, you are going inside. For now, you sit at the edge of the crack, looking down into the blue shadow. The dim sunlight catches the ice walls at angles that make them glow faintly, a blue so deep it is almost black at the bottom of the fracture, brightening to a pale, cold blue near the top. You are very tired. Not from the walk. In this gravity, even an extended walk is effortless. But from the distance, from the strangeness, from the weight of being this far from anything you recognize. Your breathing slows. Your body has carried you across the solar system, across billions of kilometers of nothing, and now it is asking you to rest. You lean back from the edge of the crack, still looking up at the faint stars visible even in the dim light of this distant sun. Saturn hangs above you, enormous, ringed, silent. Its rings catch the sunlight and spread it in a wide arc across the sky. You have never seen anything like it. You close your eyes. Beneath you, through 30 kilometers of ice, and then through kilometers of dark ocean water, and then through the rock of a primordial core, heat is moving. Slowly, patiently. The same heat that has kept this ocean liquid for hundreds of millions of years. It is not going anywhere. It will be here when you wake. Rest now. There is more to see. But not tonight. Tonight, you are on the surface of Enceladus, and the cracks are there, and the ocean is below, and everything you will find tomorrow is waiting for you, patient and cold and impossibly full of possibility. Let the sound of nothing carry you. Let the weight of distance settle over you like a blanket. You are far from everything you know, and that is, somehow, exactly where you need to be. You are still at the edge. The fracture drops away from your feet, 500 meters of layered ice wall descending into shadow, and you have not moved since you sat down. You did not mean to stay this long, but the view has held you. Saturn overhead, too large to look at all at once, its rings catching the distant sun and scattering light across the southern sky of this moon. The fracture below you, impossibly clean, impossibly straight, as if the moon cracked along a ruler. And the haze. That faint, barely visible shimmer rising from the southern horizon. You could not see it clearly last night. But now, as your eyes adjust to the dimness, as the geometry of this world becomes more familiar, you can trace it upward, a column of something, narrow and fast, rising from somewhere just out of sight. You are going to walk toward it. But first, you need to understand what you are standing on. The tiger stripes of Enceladus, named informally for their visual resemblance to the markings of a tiger when viewed from orbit, are officially designated as sulci, the Latin geological term for parallel furrows or grooves. There are 4 primary ones. They are named Alexandria sulcus, Cairo sulcus, Baghdad sulcus, and Damascus sulcus. All 4 run roughly parallel to each other, oriented approximately perpendicular to the sub-Saturn direction, the direction pointing towards Saturn. Each one cuts approximately 2 kilometers wide at the surface, and they are spaced at regular intervals of approximately 35 kilometers, center to center. That regularity is not coincidental. The spacing of the stripes reflects the mechanical properties of the ice shell itself, the way stress propagates through a material of a given thickness and stiffness. If you know the spacing, you can calculate the thickness of the ice shell in this region. Scientists have done exactly that. The south polar ice shell of Enceladus, the shell directly beneath your feet, beneath the southern plain, beneath the tiger stripes, is estimated to be approximately 5 kilometers thick. 5 kilometers. Thin for a shell of ice covering an ocean. For comparison, the average thickness of the Arctic ice sheet on Earth is only about 2 to 3 meters. The ice sheet of Antarctica averages about 2 kilometers. 5 kilometers sounds thick. But for a moon whose total radius is only 252 kilometers, a 5-kilometer shell is actually quite thin, less than 2% of the total radius. And that thinness is part of why the heat below reaches the surface. part of why the cracks exist, part of why the water escapes. You are standing at the edge of Damascus Sulcus. You checked the maps before you landed. Damascus is the southernmost of the 4 tiger stripes, and it is the one from which the most vigorous plume activity has been observed. Looking to your right, the fracture extends to the east, curving slightly as it follows the stress lines of this terrain, its far end hidden below the tight horizon. Looking to your left, it extends westward, wider in some places, narrower in others, and from somewhere along its western reach, the haze is rising. You are going to follow it to the source. You begin walking along the rim of the fracture, moving west. The surface here is not as smooth as the plane you crossed to get here. The ice near the tiger stripes has been disrupted repeatedly by the same forces that created the fractures, pushed up into low ridges, pulled apart into smaller cracks and crevasses, folded and refolded by millions of years of stress cycling. Every 32 hours, the tidal pull of Saturn changes as Enceladus moves through its slightly elliptical orbit. At its closest approach to Saturn, the tidal force is strongest. At its farthest, it relaxes slightly. That oscillation, small by the standards of planetary physics, enormous by the standards of solid ice, means the tiger stripes are never fully at rest. They are always moving, always breathing, always opening slightly and closing slightly with each orbit. And every time they open, a little more water escapes. You are watching the ground as you walk, and you notice something. There is a faint frost coating the ice near the rim of the fracture, a delicate crystalline layer, different from the older ice beneath. This frost is fresh. It has been deposited recently, within the last few orbital cycles, perhaps less. Water vapor escaping from the fracture has condensed on the cold ice of the surrounding surface and frozen into this delicate layer of crystals. You are walking through fallout from the plume, the snow of Enceladus. It is not dramatic. It does not fall in flurries or drift in winds. There is no atmosphere here for wind. It falls in perfect silence, each tiny water ice crystal following its ballistic trajectory from the plume and settling wherever gravity brings it. Over millions of years, this fallout has been the mechanism by which the southern hemisphere of Enceladus is continuously resurfaced. The craters you saw from orbit in the northern hemisphere, absent in the south because the south is constantly being buried under new material. The same process that launches water into space also gently, perpetually covers the surrounding terrain with new ice. The extraordinary reflectivity of Enceladus is maintained by exactly this process. Freshwater ice is nearly perfectly reflective, but as ice ages in space, it is slowly darkened by organic chemistry and micrometeorite gardening. On Enceladus's southern hemisphere, the ice never gets old enough to darken. Before it can, it is buried by the next layer. You have been walking for what might be 20 minutes. In this gravity, walking is effortless. Each step is a gentle push. Each landing is soft. You have barely exerted yourself. But the fracture beside you has changed. The walls look different here. Brighter. The ice on the inner walls of the crack in this section is extraordinarily pure, almost luminescent in its whiteness, catching the dim sunlight and throwing it back with a clarity that seems almost unnatural. This is where the water exits closest to the surface. The heat from the interior keeps these walls from accumulating older, darker material. They are constantly refreshed. And ahead of you now, visible without any instrument enhancement, you can see it clearly. The plume. It rises from a point perhaps 300 meters ahead, erupting from a section of the fracture where the walls are widest apart. From ground level, it does not look like the dramatic geyser that Earth's geothermal features produce. There is no column of steam, no roiling cloud of vapor at the base. Instead, it is clean and fast and almost invisible, except against the black of space above. A rush of water vapor and ice crystals launching upward at speeds your instruments confirm are approximately 1,400 meters per second. That is 1.4 kilometers per second. Faster than the speed of sound at sea level on Earth. Faster than most rifle bullets. An eruption not of lava or fire, but of cold water, launched from beneath an ice shell by forces you are standing in. You stop. You look up. The plume climbs above you, narrow at the base, broadening as it rises, the individual particles following slightly different trajectories until the column fans out into a diffuse spray hundreds of kilometers above. Above the escape velocity of Enceladus, which is only about 240 meters per second, the material in the plume escapes entirely. It does not fall back. It travels outward, spreading through Saturn's orbital space, following its own orbit around the gas giant, gradually populating the diffuse, wide ring of ice particles known as the E-ring. The E-ring of Saturn, visible in images as a faint, broad band extending from inside Mimas's orbit to beyond Rhea's orbit, is made entirely of Enceladus. Every particle in the E-ring was launched from a tiger stripe. Every ice crystal was once liquid water beneath the surface you are standing on. The rings of Saturn are partly fed by this moon. The Cassini spacecraft detected this connection in 2005 when its instruments showed that the composition of the E-ring exactly matched the composition of the Enceladus plume. Not approximately matched, exactly matched. The link between Enceladus and the E-ring was one of the most surprising discoveries of the Cassini mission, a mission that was itself full of surprises. You are now standing close enough to the plume source that you can feel its effects in your instruments, though not through your suit. The temperature of the fracture walls here, at the active section of Damascus Sulcus, reaches a maximum of approximately -93 degrees Celsius near the top of the crack. -93 degrees Celsius. That is more than 100 degrees warmer than the surrounding surface. In the context of Enceladus, that is an extraordinary differential. It is still cold by any Earth standard. Winter temperatures in Siberia or Antarctica occasionally reach -60 or 70 degrees Celsius, but even Earth's most extreme cold environments do not get to -93. But here, in a place where the average surface temperature is -201, a temperature of -93 is practically tropical. And deeper in the crack, the temperature is warmer still. The tiger stripes are not simple cracks that go straight down to the ocean. They are complex fault systems with branching fractures, with zones of compression and extension, with geometry that reflects the tortured history of a surface that has been stressed and re-stressed for hundreds of millions of years. As you approach the active vent section, you can see the geometry more clearly. The fracture here is not a clean V-shape, narrowing to a point below. It is more complex. The walls slope outward in some sections and step in others, with ledges of ice jutting out from the wall, created when sections of the wall broke away and were recoated with new material. The colors inside the fracture are extraordinary. Near the top, the walls are white, the same brilliant white as the surface. Deeper, where the angle of sunlight cannot reach, the color shifts toward a deep dimensional blue. And at the very bottom of the visible section, where the fracture descends into the darkness you cannot see, there is almost no light at all, just a darkness that is not black, but the deep blue of ice with a light source somewhere impossibly far above. You understand now, in a physical, embodied way that no photograph could have communicated, why the Cassini scientists were so astonished by the tiger stripes. They are not surface features. They are wounds. Wounds in a shell of ice, cut by forces operating from 30 kilometers below, maintained by a heat source that has been running continuously since before anything alive on Earth had yet evolved bones. The ocean below you is ancient. You do not know exactly when Enceladus's internal ocean formed. The question of when is one of the genuinely contested scientific discussions ongoing in planetary science. Some models suggest the ocean has existed for billions of years, perhaps for most of the life of the solar system. Other models suggest the current level of tidal heating, and therefore the current state of the ocean, may be a more recent development, perhaps within the last 100 million years or so. 100 million years is a strange thing to call recent, but in the context of a 4.5 billion-year-old solar system, it is. What is not contested is that the ocean exists now, and that it has existed for long enough to have shaped the surface of Enceladus in every way you can see. The Cassini spacecraft confirmed the existence of a global subsurface ocean, not just a local one beneath the South Pole, but a true global ocean surrounding the entire rocky core, in 2015. The confirmation came from two independent lines of evidence. The first was gravity data. As Cassini flew close to Enceladus on multiple flybys, scientists measured the tiny gravitational tugs the spacecraft experienced due to variations in the mass distribution below the surface. The data showed that the south polar region was gravitationally lighter than it should be if it were solid ice all the way down, consistent with the presence of a lower density liquid water layer beneath a thinner ice shell. The second line of evidence was what scientists call libration, a slight wobble in the rotation of Enceladus as it orbits Saturn. If Enceladus were a solid body, its rotation would be essentially rigid. But Cassini's observations showed that Enceladus wobbles slightly more than a solid body would, about half a degree more than expected. That extra wobble can only be explained if the outer ice shell is not coupled to the rocky core below, if there is a layer between them that allows the shell to move independently. A layer of liquid water. A global ocean locked beneath the ice, covering the entire rocky heart of this small world. You step back from the edge of the plume source. You do not want to get too close, not for safety reasons, but because the view is better from here, where you can take in the whole geometry of the vent region. The plume rises to your right, climbing into the darkness above. The fracture wall opposite you catches the dim sunlight and glows a faint, cold blue. And somewhere below your feet, at a depth your instruments estimate at 5 kilometers from the surface of the southern plain, the ice gives way to water. Not ice water, not water close to freezing. Water that, at certain depths near the rocky seafloor, is estimated to be above 90 degrees Celsius, hot enough that on Earth it would be scalding. How do scientists know this without having ever directly sampled the ocean? Because of what the Cassini spacecraft found in the plume. When Cassini flew directly through the Enceladus plume in 2008 and 2015, its mass spectrometer, the Ion and Neutral Mass Spectrometer, or INMS, analyzed the chemical composition of the plume material. The plume is not just water. It is 91% water vapor. But the remaining 9% tells an extraordinary story. The plume contains molecular hydrogen, H2. It contains carbon dioxide. It contains methane. It contains complex organic molecules, including molecules with masses above 200 atomic mass units, molecules that on Earth are only produced through complex chemistry involving energy and organic precursors. The presence of molecular hydrogen, H2, is particularly significant. On Earth, molecular hydrogen in this context is produced by a process called serpentinization, a chemical reaction that occurs when hot water contacts certain types of rock called peridotite, transforming the minerals in the rock and releasing hydrogen as a byproduct. This process is the foundation of the deep-sea hydrothermal vent ecosystems on Earth, ecosystems that do not depend on sunlight at all, but instead use the chemical energy in the hydrogen to power a food chain that exists in total darkness, miles below the ocean surface. The presence of molecular hydrogen in the Enceladus plume strongly suggests that this same process, serpentinization or something like it, is occurring at the interface between the ocean and the rocky core of Enceladus. Hot water in contact with rock, generating chemical energy, the same chemistry that on Earth feeds entire ecosystems without a single photon of sunlight. You are still looking at the plume. It rises and rises, higher than you can track with your eyes, higher than the moon's own thin exosphere, what technically passes for an atmosphere here, so tenuous that individual molecules travel in ballistic arcs without ever colliding with each other. Above the escape velocity threshold, the plume material leaves Enceladus forever, becoming part of the E-ring, part of the Saturn system, part of the quiet machinery of a ringed planet 400 million kilometers from the nearest source of biological activity. Or so you think. The plume does not feel barren. Standing this close to it, watching the silent eruption climb into the black sky, knowing what chemistry is producing it, knowing what is happening at the seafloor 5 and 30 and 100 kilometers below, you do not feel emptiness. You feel something older than that. The plume material is partially recaptured by Enceladus's gravity. The fraction launched below escape velocity falls back in a ballistic arc and lands somewhere on the surface, adding to the perpetual snowfall that keeps the southern hemisphere white and young. And the E-ring material, the fraction that escapes, eventually migrates inward towards Saturn under the influence of electromagnetic forces and gradually spirals into the planet's upper atmosphere. The E-ring has a lifetime, in astronomical terms, of only about 10,000 years before it would dissipate if Enceladus stopped feeding it. The fact that the E-ring exists means the plume has been active for at least that long, possibly much longer, possibly since before the first complex organisms appeared on Earth. This eruption may have been running since before there were animals. You're tired in a way that has nothing to do with physical exertion. The weight of timescale is doing something to your thinking. Everything here operates on scales that human consciousness is genuinely not built to hold. 100 million years. Orbital resonances. Hydrothermal chemistry. Ice shells 5 kilometers thick. You sit down on the ice, away from the edge of the fracture, within sight of the plume but no longer directly beside it. Saturn is still overhead. It has moved slightly. Enceladus moves fast in its orbit, and Saturn's apparent position in the sky shifts noticeably over the course of what would be a day. The rings are tilted differently now, catching the sun at a different angle, the shadows of the ring structures falling across each other in patterns that shift continuously. You watch the rings for a while. The A-ring, the Cassini division, the dark gap discovered in 1675 by Giovanni Cassini, the astronomer whose name was given to the spacecraft that changed everything humanity knew about this system. The B-ring, densest and brightest. The C-ring, faint and dark. And the E-ring, broadest of all, too faint to see directly from here, but extending far beyond the visible main rings, populated continuously by the eruption behind you. You feel the smallness of this moon acutely. 504 kilometers across. A world you could drive across in a few hours on an Earth highway, if there were roads, if there were vehicles, if there were anything here but ice and cracks and silence. But inside it, inside this tiny, cold, dim world, is something that defies the smallness. An ocean larger by volume than all of Earth's oceans combined. The ocean of Enceladus, estimated from gravity data and the geometry of the ice shell, contains approximately the same volume of water as Earth's oceans, possibly more. All of it liquid. All of it salt water. All of it sitting in permanent darkness, in contact with a rocky floor that is being continuously heated by forces originating in the gravity of a planet 250,000 kilometers away. You close your eyes. The plume continues behind you. You cannot hear it, no sound, but you know it is there. Still erupting. Continuous. Patient. The same water that has been circulating in that ocean for millions of years, rising through the cracks in the shell, erupting into space, falling back as snow, melting into the ocean again, cycling through. Water has memory, some people say. It is not scientifically accurate, not in any formal sense. But on Enceladus, the water does carry something. It carries the chemistry of everything it has touched. The rock it flowed over. The minerals it dissolved. The heat it absorbed from the hydrothermal vents. All of it encoded in the molecular composition of the plume, readable by an instrument sensitive enough to detect parts per trillion. The Cassini NMS was sensitive enough, and what it read was extraordinary. The complex organic molecules detected in the plume, those molecules with masses above 200 atomic mass units, were detected in the 2017 flyby data and published in 2018. They were not simple hydrocarbons. They were nitrogen-bearing organic compounds, oxygen-bearing organic compounds, molecules that in the chemical inventory of life are building blocks, not life itself. There is no scientific paper claiming that life was detected in the Enceladus plume, but the building blocks were there, in a place that has liquid water, in a place that has chemical energy, in a place that has been stable for millions, possibly billions of years. The question is not whether the conditions are right. The question is whether anything took advantage of them. The plume continues. You are sitting on the ice, back to the fracture, looking up at Saturn. Your breathing is slow. The scale of everything you are thinking about is working on you the way it always does. Not like a pressure, not like anxiety, but like a tide. Pulling back, making you smaller in the best way. Reminding you that the universe is doing most of its work without your attention. Right now, on a seafloor you cannot see, in an ocean you cannot reach, hot water is rising through cracks in rock and releasing chemical energy into the dark. It has been doing this since before the first fish evolved on Earth. It will be doing this long after you have come and gone. And somewhere in the chain between those two facts, between the heat and the ocean and the molecules and the time, something may have taken notice. Something may have learned to use it. You do not know. Nobody knows. But tomorrow you are going down. You are going through the ice. You are going to the ocean. Not tonight. Tonight, the surface is enough. Tonight, the plume is enough. The sight of it, the knowledge of it, the sound it does not make. The darkness out here is not empty. The distance is not absence. You are on Enceladus. The ocean is below you. The plume is behind you. Saturn is above you. And right now, in this moment, on this small white moon in the outer solar system, you are exactly where the story is. Sleep now. The questions will still be here in the morning. They have been waiting since before any eye existed to ask them. They can wait a little longer. Your eyes are heavy. The cold that surrounds you cannot touch you. The silence that fills this world is complete. Let it settle into you. You are far from everything familiar. You are safe. You are small in the way that stars make you small, not diminished but clarified, reduced to what you actually are. A living thing at rest on a world that is full of possibility. The plume is climbing. The E-ring is drifting. Saturn's rings are catching the distant sunlight and holding it. Close your eyes. The ocean is waiting. You said you would go down today. And now that the moment is here, you are standing at the edge of Damascus Sulcus again, looking into the fracture, and the distance below you feels different than it did yesterday. Yesterday it was a view. Today it is a path. The crack descends 500 meters to where you can see, and then the walls narrow into shadow and disappear. But your instruments have already mapped what is below the visible section. The fracture does not end at 500 meters. It continues, branching, narrowing, widening again through the full 5 kilometers of the ice shell, connecting the surface where you stand to the ocean below. Not a straight path. Not a clean vertical shaft. A network of fractures, interconnected, some wide enough to move through and some not, all of them oriented along the same stress geometry that produced the tiger stripes themselves. You have chosen a route. You begin your descent. The first 100 meters are the most visually dramatic. The walls on either side of you catch the dim sunlight from above and scatter it in a way that makes the ice glow. A cold, deep blue on the shadowed wall, a brighter, colder white on the wall that faces upward. The layering is extraordinary up close. You can see individual strata in the ice, horizontal bands of slightly different density or composition, each one representing a period in the history of this fracture. Periods when more material was deposited. Periods when the fracture closed slightly under compressive stress and new ice formed from water vapor condensing on the walls. Periods when something happened at depth that changed the chemistry of what was rising through the crack. The layers are not perfectly horizontal. They tilt and curve with the geometry of the fracture, following the stress history of the ice shell rather than any gravitational reference. You pass the first 100 meters. The light from above is still present but diminished. The blue deepens. At 200 meters below the surface, the walls are close enough that you could touch both sides simultaneously with outstretched arms in the narrower sections. The fracture here has a different character than it did near the surface. The surface sections of the tiger stripes have been processed by the constant cycling of water vapor, material rising from below, condensing, redepositing, forming the bright, fresh ice that gives Enceladus its extraordinary reflectivity. But here, at depth, the ice has a different texture. It is older, denser. The surface you would touch if you reached out would feel hard and slightly granular, not the soft, fluffy texture of fresh snow, but something closer to the blue ice of a glacier, compacted by the weight of everything above it. At 300 meters, you pass what your instruments identify as a significant change in the fracture geometry. The crack widens. Not dramatically, perhaps doubling in width over the course of 10 vertical meters, but the widening is associated with a change in temperature. The walls here are warmer. Negative 140 degrees Celsius. Still cold. Still far below any temperature that would support liquid water, but warmer than the surface by 60 degrees. Heat from below is rising through the fracture system, conducting through the ice walls and warming the void inside the crack. You keep descending. The light from above is a pale glimmer now, visible if you look up, but not providing any useful illumination at this depth. You are in the dark of the fracture, moving by instrument. The temperature continues to rise with depth. At 1 kilometer below the surface, your instruments read negative 112 degrees Celsius. At 2 kilometers, negative 78. At 3 kilometers, the ice walls around you are negative 40 degrees Celsius, still below the freezing point of pure water, but well within the range of temperatures that occur in the most extreme environments on Earth's surface. The fracture has changed dramatically. At the surface, the tiger stripes are clean, sharp features. Here, at 3 kilometers depth, the fracture has become something more complex, a series of interconnected chambers, some large enough that the walls are not visible simultaneously, connected by narrower passages that represent different episodes of fracturing in the ice shell's history. You pause in one of the larger chambers. The geometry of this space is extraordinary. The walls are not flat, they bulge and curve in 3 dimensions, reflecting the way the ice fractured under stress rather than being cut by any tool. The ceiling of the chamber is perhaps 30 meters above you. The floor beneath you is ice, older, denser, darker in color due to the reduced light and the different chemistry of ice formed under pressure. And the walls. The walls here are not the brilliant white of the surface ice. They are darker, tinged with something. Your instruments identify trace quantities of organic molecules on the wall surfaces. Not a lot, not a concentration that would be visible to the naked eye, but detectable. Organic compounds, carbon-bearing molecules deposited on the walls of this chamber from the water vapor and ice particles that have passed through here over millions of years. The chemistry of the ocean below is written on these walls, faintly, in molecules too small to see. You are reading a record of what is below. You continue downward. At 4 kilometers, the temperature is -8 degrees Celsius. Close to freezing. Your instruments are detecting more water vapor in the fracture now, not the thin traces of the upper sections, but a measurable humidity, water vapor rising from below in quantities that suggest you are approaching the interface between the ice shell and the liquid ocean. The ice walls at 4 kilometers look different. They are not the hard, ancient ice of the middle sections. They are what glaciologists call temperate ice. Ice that is close to its melting point, slightly plastic, deforming slowly under its own weight. In the walls around you, the ice is barely holding its structure. And at 4.5 kilometers, it begins to give way. The walls of the fracture at this depth are not ice. They are slush, a mixture of ice crystals and liquid water, the boundary phase between the solid shell above and the liquid ocean below. The precise transition depth varies across Enceladus. In the south polar region, under the tiger stripes, the ice shell is thin, perhaps 5 kilometers, and the heat flux from the hydrothermal activity below is high enough to depress the melting point transition to near this depth. In other regions, under the thicker ice of the northern hemisphere, the ice-ocean interface is deeper. But here, under Damascus Sulcus, the ice is almost gone. You descend through the slush layer. It takes perhaps 10 minutes. And then, at a depth of approximately 5 kilometers below the surface of Enceladus, the walls of the fracture disappear. You are no longer inside a crack. You are in open water. The ocean of Enceladus. Stop. Let that settle. You are in the ocean of Enceladus. Above you, 5 kilometers of ice. Below you, an ocean estimated to be at least 10 kilometers deep, possibly much deeper depending on which model of the interior you use, extending all the way down to a rocky seafloor that is in direct contact with the liquid water at your level. The water around you is not clear. It is slightly turbid, not muddy, not opaque, but carrying a fine suspension of particles that scatter the faint bioluminescence. Not biological, not here, not yet, but the faint chemical luminescence of minerals in solution, of trace elements that catch what little light exists at this depth. There is almost no light. The bioluminescence, the mineral luminescence, is extremely faint. Your eyes, fully adjusted to darkness, would see almost nothing, but your instruments see clearly, The temperature of the water around you is approximately 2 degrees Celsius. Cold. Not freezing, the salt content of this ocean, estimated from the composition of the plume, keeps the freezing point of the water below 0 degrees Celsius. But cold. The salinity of the Enceladus Ocean is estimated from the plume data to be roughly similar to Earth's oceans, perhaps 3 to 4% salt by mass, though with a different mix of dissolved minerals than Earth's seawater. The pH of the water at this depth is approximately 11 to 12. That is highly alkaline, more alkaline than bleach, more alkaline than almost any natural water body on Earth, except for some highly specific environments like soda lakes in East Africa, where certain microorganisms have evolved to survive. The alkalinity is a product of the water-rock interactions at the seafloor. Water reacting with silicate rock in the serpentization process produces hydroxide ions, raising the pH. In Earth's deep-sea hydrothermal vent systems, the water near the vents can reach similarly high pH levels. And at those vents on Earth, life thrives. You descend further into the ocean. The water pressure around you increases with depth, approximately 1 atmosphere for every 10 meters of water depth. At 1 kilometer depth in this ocean, you are under roughly 100 atmospheres of pressure. For comparison, the pressure at the bottom of the Mariana Trench on Earth, the deepest point in any ocean on our planet, is approximately 1,096 atmospheres. The ocean of Enceladus, at its deepest, may approach similar pressures. Pressure by itself is not a barrier to life. On Earth, microorganisms have been found at every depth of the ocean, including the most extreme pressures of the deep trenches. Life has evolved molecular machinery, proteins with modified structures, membrane lipids with different compositions that allow cells to function under pressures that would destroy the cellular machinery of surface organisms. Pressure is not a wall. You descend. At 5 kilometers depth in the ocean, the water temperature begins to change. It is warming. Not dramatically, not suddenly, but the instruments show a clear, steady increase, 2 degrees, then 4, then 8, then 15. You are approaching the seafloor. The seafloor of Enceladus, the boundary between the liquid ocean and the rocky core, is one of the most scientifically significant surfaces in the solar system. It is the place where the heat comes from. The core of Enceladus is rocky, composed primarily of silicate minerals, remnants of the same processes that built the terrestrial planets in the inner solar system. The core radius is estimated at approximately 190 kilometers, most of the total radius of the Moon. The ice shell and ocean above it represent only the outer 60 kilometers. The core is not cold and dead. The same tidal heating that keeps the ocean liquid, the flexing of the rock under Saturn's gravitational gradient, also maintains hydrothermal activity at the core-ocean interface. Warm water circulates through fractures in the seafloor rock, reacting chemically with the minerals it contacts, picking up dissolved compounds, releasing molecular hydrogen and other products of serpentinization, and then rising as hot plumes through the ocean water. You descend toward the seafloor, and then you see something. Faint at first. A glow. Not the mineral luminescence of the mid-water column. Brighter. Warmer in color, not blue-white, but orange-yellow, the color of heat. A hydrothermal vent. You approach slowly. The water temperature climbs rapidly as you near the vent, 15 degrees, 40, 70, 90. At the vent itself, the temperature is estimated to exceed 90 degrees Celsius, scalding by Earth's thermal standards. The vent is not a dramatic structure, not at first. It is an opening in the rocky seafloor, perhaps 2 meters across, from which water is rising in a column. Not steam, the pressure prevents boiling, but superheated liquid water, rising in a turbulent column that shimmers and distorts the view of everything behind it. Around the base of the vent, the rock is encrusted with mineral deposits, silica, carbonate, sulfide minerals precipitated from solution as the hot vent fluid met the cooler ocean water. These deposits are what Cassini's instruments detected as nanosilica particles in the Enceladus plume. Silica particles, formed at the hydrothermal vent, carried upward through the ocean through the fractures in the ice shell and erupted in the plume, where a spacecraft 400 million kilometers from Earth intercepted them and identified them as evidence of ongoing hydrothermal activity. The particle size of the silica was significant. The nanosilica particles in the plume were between 4 and 16 nanometers in diameter. Laboratory experiments on Earth showed that particles of this size can only form and remain stable in hot water above 90 degrees Celsius for a limited time before they aggregate into larger particles. The fact that nanosilica of this specific size was present in the plume meant that the hot water had traveled from the seafloor to the surface in less than a few years. The hydrothermal system is active. It is not a remnant of some ancient heating event. It is running right now. Right now, as you are watching this vent, the same chemistry is happening here as it happened 4 billion years ago, when the first life on Earth was beginning. You sit near the vent, not directly in the superheated outflow, but in the warmer water nearby, where the temperature is around 30 to 40 degrees Celsius. The water here carries everything the ocean knows. Dissolved silica, dissolved carbonate minerals, molecular hydrogen, freshly produced by the serpentization reaction happening in the rock below the vent opening, carbon dioxide, methane produced possibly by the same reaction, or possibly by something else. Methane on Earth is overwhelmingly produced by biological processes. Methanogenic archaea, single-celled microorganisms, are responsible for almost all of the biological methane on Earth, and they thrive in exactly these kinds of oxygen-poor, hydrogen-rich, warm, alkaline environments. The methane in the Enceladus plume could be produced abiotically by chemical reactions between carbon-bearing minerals and hot water. It could also be produced by methanogenic microorganisms in the ocean. Scientists have modeled both possibilities. A study published in 2021 in the journal Nature Astronomy modeled whether the methane detected in the Enceladus plume could be explained entirely by abiotic chemistry, and found that the concentration was higher than expected from purely chemical processes alone. That does not mean life is responsible. There are other possible explanations, but it is a measurement that demands explanation. The vent in front of you continues its quiet, patient eruption. Hot water rises. Minerals precipitate. Chemical energy is generated. The ocean receives it all. You look at the seafloor around the vent. The rock is dark, basaltic or peridotaic in composition, the same silicate minerals found in Earth's mantle and the floors of Earth's deepest oceans. On Earth, the rock around hydrothermal vents is colonized. Within meters of a vent belching water hot enough to kill most organisms, you find communities of extremophile bacteria and archaea, chemolithotrophs, organisms that derive energy not from sunlight and organic carbon, but from the chemical energy in inorganic compounds. They oxidize hydrogen. They reduce sulfate. They consume methane. They fix carbon dioxide into organic molecules using only the energy of chemical bonds. They are the foundation of an entire food web, one that includes tube worms 2 meters long, crabs adapted to darkness, shrimp with light-sensing organs on their backs, fish that have never seen sunlight and never need to. None of that is visible here. If there are microorganisms around this vent, and there may not be, they are invisible. A single cell is 1 to 10 micrometers in size. Even a colony of billions of cells would be invisible to the unaided eye unless it formed a biofilm, a mat, a macroscopic structure. You cannot see biology here. You can only see chemistry. And chemistry here looks exactly like it looks in the places on Earth where life is most tenacious and most unexpected. You are sitting in the conditions for life. The ocean continues around you. You are aware of the scale of it, not just the depth but the breadth. The ocean of Enceladus surrounds the entire rocky core. It is a global ocean. In every direction from where you float near this vent, the ocean extends across the seafloor, over the tops of other vents you cannot see, through colder, darker water far from any heat source, all the way to the underside of the ice shell above. The total volume of this ocean is estimated at approximately 1 × 10 to the 19th liters, comparable to, and possibly greater than, the total volume of Earth's oceans combined. All of it liquid. All of it salt water. All of it sitting in complete darkness, warmed from below, cooled from above, circulating under the influence of the hydrothermal activity you are watching right now. The circulation of the Enceladus ocean is driven by the same principle as convection in any fluid. Warmer water rises, cooler water sinks. Hot water from the vents rises, carrying heat and dissolved compounds upward through the water column. Cooler water near the ice-ocean interface sinks, replacing the water that has risen. The timescale of a complete circulation cycle, from vent to surface and back, is estimated to be on the order of tens of thousands of years. Tens of thousands of years of continuous mixing. In that time, any chemistry happening at the seafloor has the opportunity to spread through the entire ocean. Any byproduct of any reaction at any vent eventually reaches the ice-ocean interface, and if it is volatile enough, enters the fracture system and eventually the plume. This is how Cassini was able to sample the chemistry of the Enceladus seafloor from orbit. The ocean is the messenger. The plume is the delivery system. The spacecraft was the instrument. And the message was, this place has everything. Everything. You are getting cold. Not physically, but the cognitive cold of a question that cannot be resolved. You know what is here. You know the chemistry. You know the conditions. You know what analogous conditions produce on Earth. and you still do not know the answer. No one does. Not yet. You begin to rise, slowly, ascending through the water column back toward the ice above. The hydrothermal vent diminishes below you. The glow of it fades. The temperature drops as you ascend. At 3 kilometers above the seafloor, the water is cold again, close to 2 degrees Celsius. The particles in suspension catch the faint light from above, the light that filters down through the ice from the dim sunlight on the surface. Not much light. Almost none. But enough that at 1 kilometer below the ice ceiling, you can begin to see the underside of the shell. And the underside of the ice shell of Enceladus is extraordinary. It is not flat. It is not a smooth, uniform surface. It is a landscape. The bottom of the ice shell has been shaped by the same forces that shaped the top, by the stresses and fractures and refreezing events that have operated on this moon across geological timescales too long to hold in mind. There are ridges on the underside of the ice corresponding to the ridge systems on the surface. There are deep troughs where the fractures penetrate, where the ice is thinnest, where the ocean is closest to the surface. And directly above the tiger stripes, the ice ceiling is not just thin. It is actively melting from below as the warm water near the vents circulates upward and contacts the base of the ice shell, and simultaneously refreezing as the colder water from depth replaces it. A continuous cycle of melting and freezing at the ice-ocean interface, part of the circulation that keeps the whole system in its extraordinary steady state. You ascend through the ice ceiling, back into the fracture system, back through the slush layer at the base of the solid ice, back through the dense, ancient ice of the middle crust, back upward through the blue-black darkness of the fracture toward the faint glimmer of sunlight at the top. You're tired, not with the tiredness of exertion, with something deeper. The tiredness of having been somewhere that is genuinely, completely outside the frame of ordinary human experience. You have been in the ocean of another world. You have seen a hydrothermal vent on a moon of Saturn. You have floated in water that has never been touched by sunlight, that has been circulating in darkness for millions of years, that carries in its chemistry the record of everything that has happened at the seafloor since the ocean formed. You emerge from the fracture into the surface light, the dim sun, the white plain, the plumes still rising from Damascus Sucus, unchanged, patient, continuous. Saturn overhead, the rings, the silence. You sit down on the ice. You do not think about anything in particular. You let the scale of it work on you slowly the way it does. The way distances work on you when you look at stars. The way time works on you when you hold a fossil. This ocean has been here. This water has been moving. This heat has been rising from this rock for longer than complex life has existed on Earth. Whether or not anything lives in it, that is extraordinary. Whether or not anything is down there looking back, that ocean exists. It is real. The data confirmed it. The chemistry corroborated it. The spacecraft measured it from hundreds of kilometers away, and the numbers were unambiguous. Liquid water, chemical energy, organic molecules, a stable environment, hundreds of millions of years. These are not the words of hope. They are the measurements of science. And science tonight has brought you to the edge of the greatest question in planetary biology. Close your eyes. You have been deep today, deeper than you have ever been. And now it is time to let the depth carry you somewhere else. Let the weight of the water above you become the weight of sleep. Let the darkness of the ocean become the darkness behind your eyes. Let the slow circulation of cold water through an ancient, lightless sea become the slow rhythm of your breathing. In, out. The vent is still glowing somewhere below. The water is still moving. The molecules are still drifting through the dark. You do not need to watch it. It will continue without you. It has been continuing without anyone watching for a very long time. Rest now. The ocean does not need your attention to continue. The chemistry has its own direction. It always has. You have been thinking about the question since you came back to the surface. It followed you up through the fracture, through 5 kilometers of ice, through the slush and the ancient compressed layers, and the blue-black dark of the upper crack. It was waiting for you when you emerged into the dim sunlight of the southern plain. It is still here now. Not a question you can answer. Not a question anyone can answer yet, but a question with weight. Is anything alive in that ocean? Not in the abstract way the question is sometimes asked, not as a philosophical musing about the probability of life in the universe. In the specific, concrete, measurable way. Is there, right now, in the ocean beneath your feet, any organism, any cell, any structure, any process that meets the biological criteria for life? Metabolism, reproduction, response to environment. Is there anything down there doing those things? You do not know. Nobody knows. And before you can think clearly about what it would mean to find the answer, you need to understand what it would even take. Let us start with what life requires. In astrobiology, the scientific discipline concerned with the origin, distribution, and future of life in the universe, scientists have identified a minimal set of conditions that appear necessary for life as we know it. Liquid water, a source of energy, a set of chemical elements typically summarized as CH-NOPs, carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. These are not arbitrary choices. They reflect what life on Earth is actually built from. Every cell on Earth, every bacterium, every archaeon, every eukaryote is built from carbon-based molecules assembled in liquid water, powered by chemical or light energy, and requiring the CH-NOPs elements in its biochemistry. There are speculative arguments for alternative biochemistries, life using silicon instead of carbon, life using liquid methane instead of water as a solvent, as might potentially exist on Titan. But these remain speculative. For the question of Enceladus, we are asking about life as we know it. And for life as we know it, the first condition, liquid water, is unambiguously satisfied. The second condition, energy, is satisfied by the hydrothermal system. The third condition, CH-NOPs elements, is addressed by the plume data. Carbon confirmed in CO2, methane, and complex organic molecules. Hydrogen confirmed as molecular H2 and in water. Nitrogen detected in nitrogen-bearing organic compounds in the plume. Oxygen confirmed in water and CO2. Phosphorus? This is the one genuine uncertainty. Phosphorus has not been directly detected in the Enceladus plume. This is not necessarily evidence that it is absent. The instruments on Cassini were not specifically optimized for phosphorus detection at the concentrations that might exist in the plume. Phosphorus is abundant in rocky bodies throughout the solar system. It is a component of common mineral classes, and models of the geochemistry of Enceladus's seafloor suggest that water-rock interactions should dissolve phosphorus-bearing minerals and release phosphate into the ocean. A study published in 2023, analyzing the Cassini plume data with new techniques, found evidence consistent with dissolved phosphate in the ocean at concentrations sufficient to support life. The lead authors of that study stated that if their interpretation is correct, Enceladus satisfies all known requirements for life. All of them. Sulfur, also not directly confirmed, but geochemical models suggest it should be present from the alteration of sulfide minerals in the seafloor rock. The CH-NOPS checklist, as best as current data allows, appears to be complete. Every box checked. You are sitting on the ice looking up at Saturn, and you are thinking about what that means. It means that the question of life on Enceladus is not the question of whether the environment could support life. The environment almost certainly could. The question is whether life actually got started. And that is a very different question, because we do not know how life starts. We know that it did start at least once on Earth. We know the approximate time within the first billion years of Earth's existence, and possibly much sooner. We know some of the conditions: warm, wet environments with chemical gradients, where simple molecules could accumulate, react, and over time build something more complex. There are leading hypotheses. The hydrothermal vent hypothesis, the idea that life originated at alkaline hydrothermal vents on the early Earth's seafloor, is one of the most well-supported frameworks in current origin of life research. In this hypothesis, the mineral surfaces of the vent chimneys served as scaffolding for the first chemical reactions, concentrating molecules, catalyzing reactions, providing chemical gradients that could drive the formation of more complex structures. The first cells, in this view, were not the product of a single lucky event. They were the product of continuous chemistry in an environment that provided energy and substrates in a steady, sustained way. The environment of the Enceladus seafloor is in many ways analogous to the hypothesized environment of early Earth's deep-sea vents. Alkaline pH, temperature gradients from hot vent fluid to cooler ocean water, mineral surfaces in contact with hydrogen-rich, carbon-bearing fluid. If the hydrothermal vent hypothesis is correct for the origin of life on Earth, and current scientific consensus increasingly supports it, then the Enceladus seafloor is in principle exactly the kind of place where life might have started. Might have. Not did. The difference between those two words is the entire problem. We know what the conditions are. We do not know what the threshold is. The threshold, the point at which chemistry becomes biology, at which reactions become metabolism, at which self-replicating molecules become organisms, is the deepest unsolved problem in all of science. It has occupied some of the greatest biochemists and evolutionary biologists of the past century, and it remains unsolved. Not for lack of trying. Experiments in prebiotic chemistry have successfully synthesized many of the molecular building blocks of life under conditions believed to resemble the early Earth: amino acids, nucleotides, lipid-like molecules, short polymers. But the gap between a set of molecular building blocks and a living cell is still enormous, and filling that gap step by step, experimentally, remains one of the central challenges of modern science. What this means for Enceladus is profound. Even if every chemical condition for life's origin is present, and the data suggests they may be, we cannot know whether life actually arose without going there and looking. Not going as an instrument on a spacecraft flying by. Going with instruments specifically designed to detect life. Instruments that can look for cells, for cell membranes, for nucleic acids, for the specific isotopic ratios that biological processes produce, for the molecular chirality, the handedness of biological molecules that is a near universal signature of life on Earth. And so we return always to the missions. The Cassini spacecraft, which arrived at Saturn in 2004 and operated for 13 years until its deliberate destruction in September 2017, was not designed to detect life. It was not designed to look for cells or biomarkers. It was designed to characterize the Saturn system comprehensively. And in doing so, it discovered something that changed the scientific conversation entirely. Before Cassini, Enceladus was a small, unremarkable icy moon. After Cassini, it was one of the most astrobiologically significant bodies in the solar system. Cassini flew through the Enceladus plume 23 times. Each flyby added data, compositional measurements, temperature profiles, particle size distributions, velocity measurements. The final close flyby of Enceladus on October 28, 2015, was the deepest. Cassini passed within 49 kilometers of the surface, directly through the densest part of the plume, collecting the richest data set of any single flyby. The data from that flyby included the molecular hydrogen detection that confirmed ongoing hydrothermal activity. It was, in many ways, the moment that transformed Enceladus from a curiosity into a priority. But Cassini had a fundamental limitation. Its instruments were not life detectors. The organic molecules it found were important clues. But clues are not answers. What would a dedicated life detection mission to Enceladus look like? Several concepts have been proposed and studied by planetary scientists and mission designers. The most comprehensive is a concept called Enceladus Orbalander, a spacecraft that would orbit Enceladus and then land on its surface, designed to directly sample the plume material and analyze it with instruments specifically optimized for biosignature detection. The Orbalander concept was studied in detail and included in the 2023-2032 Planetary Science Decadal Survey, the document produced by the National Academies of Sciences that sets the priority list for NASA's planetary science program for the next decade. The Decadal Survey ranked an Enceladus mission as a high-priority large mission for the next decade. High priority. The scientific community has spoken clearly about where this question sits. They know what is down there, and they want to go back. The Orbilander concept would carry instruments including a mass spectrometer, far more sensitive than Cassini's INMs, capable of detecting complex biomolecules at parts per trillion concentrations. A microscope capable of imaging objects at the micrometer scale, the scale of individual cells. A gas chromatograph for separating and identifying volatile organic compounds. An instrument for measuring molecular chirality, the handedness of organic molecules. And instruments for measuring isotopic ratios, particularly the carbon-13 to carbon-12 ratio, which biological processes alter in characteristic ways. With these instruments, a plume sample that contains even a small number of cells, even dead cells, would be detectable. The information content of a dead cell is enormous. The proteins, lipids, nucleic acids, and metabolic products preserved in a dead cell are all biosignatures, all signatures of biological processes that leave chemical fingerprints distinguishable from abiotic chemistry. If the Enceladus ocean contains life, and if that life is anything like life on Earth in its basic biochemistry, and if even a small number of cells or cell fragments make it into the plume, an instrument like the Orbilander's microscope would see them. And there is reason to think plume sampling would be effective. Models of the Enceladus plume show that material from the near-vent environment is efficiently transported to the surface through the fracture system and launched into space. If life exists near the vents, which is where, by analogy with Earth, it would most likely be, its byproducts should be present in the plume. The residence time of plume material, the time it takes for water from the seafloor to travel through the ocean, enter the fracture, and be launched into space, is estimated to be on the order of years to decades. Short enough that the chemical signature of seafloor processes is largely preserved. Short enough that intact organic molecules from the deep ocean reach space intact. Short enough, possibly, that intact cells could make the journey. The answer may already be in the plume, waiting to be read by the right instrument. You are thinking about this as you sit on the surface of Enceladus? The plume behind you still rising. Damascus sulcus still glowing on your instruments. The ocean below still circulating. The timeline is what gets you. The distance between now and an answer. Even if a mission were approved tomorrow, even if the political and budgetary machinery of space exploration moved with unusual speed, the earliest a dedicated Enceladus mission could reach Saturn would be in the late 2030s or early 2040s. A decade or more. And this is not unusual in the history of space exploration. Cassini took 7 years to reach Saturn after launch. The James Webb Space Telescope spent nearly 25 years in development and construction before launch. The long timescales of space exploration are not failures of ambition. They are the product of the extraordinary difficulty of building machines that must work perfectly in environments that will destroy them if they fail, at distances where no repair is possible. But the waiting is real. The question is real. And the question has been sitting here in the dark beneath this ice for longer than anything on Earth has been alive. On Earth, the oldest undisputed microfossils, the oldest direct evidence of cellular life, date to approximately 3.5 billion years ago. Stromatolites, formed by communities of cyanobacteria, preserved in ancient Australian rock formations. 3.5 billion years ago, life was already complex enough to form communities, to build structures, to leave traces in the geological record. The origin of life, the transition from chemistry to biology, happened earlier than that. Estimates based on molecular clock analyses and geochemical evidence suggest that the last universal common ancestor of all life on Earth, the single ancestor from which every organism alive today descends, lived approximately 3.8 to 4 billion years ago. Perhaps earlier, the Earth itself is 4.5 billion years old. Life, it appears, did not wait long after the conditions were right. And if life did not wait long on Earth, if it arose within a few 100 million years of the planet's formation, in an environment not drastically different from Enceladus's current seafloor, then the timescale question for Enceladus is an interesting one. How long has Enceladus's ocean been liquid? Models suggest at least several 100 million years, possibly billions. If the same speed of life's emergence applied here, if chemistry became biology within a few 100 million years of the ocean's formation, then life, if it is here, has had an immense stretch of deep time to develop. Hundreds of millions of years. In 3.5 billion years on Earth, life went from single cells to blue whales and redwood trees and the human brain. What might that span of geological time produce in the dark, under the ice, in the vents and the cold water of an ocean that has never seen the sun? We do not know. We cannot know. Not from here. Not yet, but the question has weight. You lie back on the ice of the southern plain. The surface beneath you is cold, -200 degrees, but you cannot feel it. You are looking up at Saturn. It fills a substantial portion of the sky from Enceladus, not the whole sky, but a large, unmistakable presence, its rings tilted to show their structure. You are aware of how many worlds are in this system. Saturn's 83 confirmed moons orbit at various distances. Titan, larger than Mercury, with a thick nitrogen atmosphere and methane lakes on its surface, orbits at a distance of approximately 1.2 million kilometers from Saturn. Mimas, heavily cratered, with an impact basin so large it nearly shattered the moon, orbits closer than Enceladus. Dione and Rhea orbit in the middle distances. And Iapetus, with its extraordinary two-toned coloring, orbits far out, one face perpetually bright and one perpetually dark. Each of these worlds is a place. A real place with its own physics, its own chemistry, its own history. And among all of them, Enceladus is the one that has an ocean. A warm one, a chemically rich one. Among all the moons of Saturn, and by extension among many of the known potentially habitable environments in the solar system, Enceladus has what might be the most hospitable interior. Europa, the ice-covered moon of Jupiter, also has a subsurface ocean. It is larger. Europa's ocean may contain twice as much water as all of Earth's oceans combined. And Europa is also a target of intense scientific interest, with a dedicated mission. The Europa Clipper, launched in October 2024, now en route. But Europa's ocean is farther from its rocky seafloor, and the evidence for active hydrothermal venting is less direct. Enceladus has the plume, a direct sample of its ocean continuously erupted into space. No other ocean world in the solar system offers this. No other moon is actively sampling its own interior for visiting spacecraft. Enceladus is offering you the answer. You just need the right question to ask it with. There is another dimension to this question that is easy to overlook. Not whether life exists on Enceladus, but whether, if it does, it is related to life on Earth. This is not as strange a question as it sounds. The theory of panspermia, the hypothesis that life or its precursors can travel between planetary bodies, has been a serious scientific idea since the 19th century and has gained renewed attention in the era of astrobiology. Rocks are regularly exchanged between planets and moons throughout the solar system. When a large meteorite strikes a body with a solid surface, the impact can eject material at velocities exceeding the escape velocity of that body. That material then travels through space and may eventually land elsewhere. On Earth, we have found meteorites from Mars, rocks blasted off the Martian surface by ancient impacts, traveling through space for millions of years and landing on Earth. The most famous is ALH 84001, a Martian meteorite found in Antarctica in 1984, which generated significant controversy in 1996 when NASA scientists reported possible evidence of microfossils in its structure, a claim that remains contested but not definitively refuted. Material exchange between bodies in the outer solar system is also possible, though the dynamics are different. If life originated on one ocean world, on Earth's early ocean, or on Enceladus, or on Europa, could it have traveled to another? The answer depends on whether the microorganisms could survive the journey. Some microorganisms on Earth are extraordinarily resistant to the conditions of space travel. Deinococcus radiodurans, sometimes called the most radiation-resistant organism on Earth, can survive doses of radiation thousands of times higher than would kill a human. Certain bacterial spores can survive the vacuum of space. Some organisms have been shown to survive re-entry heating when shielded by a rock matrix. The possibility that life, once it starts somewhere, could seed other environments is real. And it has a profound implication for how we interpret any discovery on Enceladus. If life is found on Enceladus, the first question will not simply be, is it alive? It will be, is it ours? Do the organisms on Enceladus share the same basic biochemical architecture as life on Earth? The same genetic code? The same chirality of amino acids? The same core metabolic pathways? If they do, if the life on Enceladus is recognizably related to Earth life, it could mean that life traveled between the two environments, seeded by ancient impact events. Or it could mean that the same chemistry in similar environments converges on similar solutions. If they do not, if the life on Enceladus uses a genuinely different biochemistry, it would be the strongest possible evidence that life is not a one-time event. That wherever conditions allow, chemistry finds a way to cross the threshold into biology. That life is not a miracle. That it is a process. This is what a second example of life would mean for everything. It would not simply mean that Enceladus is inhabited. It would mean that life is not special, that it is ordinary, that wherever liquid water flows over warm rock, wherever chemical gradients exist, wherever energy is available and time is long enough, the molecules find a way to organize themselves into something that persists and reproduces and responds. The entire history of philosophy and religion has arguments that will need to be revisited if that is true. The entire framework of how we understand our place in the universe will shift. Not vanish, but shift. Become larger, more generous, more extraordinary in its ordinariness. And it might all start here, on this small, cold, white moon, on a seafloor no one has ever seen. The light around you is changing. Enceladus orbits Saturn every 32 hours, and in that rotation, the geometry of sunlight on the southern plane shifts. Shadows lengthen and shorten. The angle of Saturn in the sky changes. The rings catch the light differently at different orbital positions. You have been here long enough to see the sky change. Long enough for the sameness of the surface, the white, the cold, the silence, to become familiar. There is a kind of peace in the sameness, in knowing exactly what the temperature is, in knowing exactly how far away Saturn is, in knowing to within a few percent how thick the ice is beneath you and how deep the ocean below that. The uncertainty is all in what is alive in that ocean. Everything else is known or knowable or being measured right now by instruments we have sent. The uncertainty is the most interesting part. You breathe slowly, or you would in a place where breathing were possible. You move with the rhythm of the question. In, out. The plume rises behind you. The ocean circulates below. The vents glow on the seafloor, patient and hot, their chemistry unchanged since before your species existed. They will be doing the same thing tomorrow, and next year, and in 100 years, when the first missions arrive to look for what you have been thinking about. And in 1,000 years, whatever those years hold. The universe does not wait for us to be ready. It simply continues. The ocean of Enceladus has been continuing for a very long time. And tonight it continues while you rest. Let the cold surface hold you. Let the distant sun provide its faint, steady light. Let Saturn's rings drift overhead in their slow, ancient geometry. You have thought about everything there is to think about today. The conditions, the chemistry, the missing instruments, the missions not yet launched, the question not yet answered. You have held all of it. Now let it go. The ocean doesn't need you to watch it. It has been running without a witness for longer than complex life has existed on Earth. Let the time scale be the thing that holds you. Let the deep time of this place, the vast uncounted stretch of water moving in the dark, of vents glowing on the seafloor, of plumes erupting and falling and erupting again, let all of that become the rhythm you fall asleep to. Not because it is comforting in the way that familiar things are comforting, but because it is real. And real things at sufficient scale have a weight that is indistinguishable from rest. The question is still there. It will be there tomorrow. It has been there since before your species had language to ask it. It can wait one more night. Your eyes are heavy. The surface of Enceladus is cold and white and silent. Saturn is above you. The rings are catching the sun. The plume is rising. And somewhere, 5 kilometers down, in a lightless ocean that has never been visited, that may or may not be inhabited, water is moving slowly in the dark. Let that be the last thing you think about. Water moving slowly in the dark. In. Out. Let the dark take you. The morning, if you can call it that on a world with no atmosphere and a 32-hour orbit, arrives not as light, but as a change in angle. The sun has moved across the sky of Enceladus while you rested. Or rather, Enceladus has moved around Saturn, and the geometry of the sun has shifted accordingly. Saturn has rotated too, once every 10 hours and 33 minutes, its banded clouds moving in long parallel streams, its rings catching the sunlight from a slightly different angle than when you closed your eyes. Everything out here moves. Everything turns. Nothing is still. You have been on the surface of Enceladus for what would be days, in Earth terms, long enough for the strangeness to have settled, long enough for the white plain and the dim sun and the immense ringed planet overhead to have become in some small way familiar. And today is the last day. Not because anything is ending. Enceladus will continue. The plume will continue. The ocean will continue. The vents will glow on the seafloor, and the molecules will drift through the cold water, and the ice shell will flex with every orbit, and all of it will be exactly as it is now, long after you have gone. Today is the last day because there is a spacecraft waiting for you, and because there are things you have not seen yet, and because the story of this moon is longer than any single visit can contain. You have one more thing to do before you leave. You want to watch the plume from above. You rise from the surface. In the near-zero gravity of Enceladus, rising does not require much. A gentle push from your thrusters, and you ascend, slowly at first, then faster, the surface falling away below you as you climb. The southern plain spreads out. At 1 kilometer altitude, the 4 tiger stripes are clearly visible, 4 dark parallel lines crossing the white surface, each one glowing faintly in infrared, each one emitting plumes that, from this altitude, you can begin to see as distinct structures. There are not 4 plumes. There are dozens. The Cassini spacecraft's imaging science system resolved, at its best resolution, at least 100 individual jet-like sources along the tiger stripes, discrete points of eruption, each one a specific location along the fracture system where the conditions are right for water to escape. 100 individual jets all running simultaneously. From orbit, they merge into a single coherent plume. But from here, at low altitude, you can see the individual sources, each one a narrow column of water vapor and ice crystals, rising from a specific point along the glowing fractures below. You continue to rise. At 10 kilometers altitude, the tiger stripes are still clearly visible, but the individual jets have merged into broader plume structures, 4 columns, one from each stripe, rising together and mixing as they climb. At 50 kilometers, the surface of Enceladus has become a disk below you, a white sphere, perfectly smooth-looking from this height, the tiger stripes reduced to faint dark lines near the South Pole. And rising from the South Pole, rising above the surface, climbing through the space around you, the plume. From here, inside it, you can see what no surface view could show. The plume is not a column. It is a fountain. The material erupts upward from the surface and then fans outward, following the ballistic trajectories of individual particles, each one launched at a slightly different velocity and angle, each one following its own path through the vacuum. Some particles are launched fast enough to escape Enceladus entirely. They travel outward and eventually enter the E-ring, joining the billions of other ice crystals already circling Saturn in that diffuse, luminous band. Other particles are launched more slowly. They rise to various heights and then fall back, tracing arcs above the surface, before landing as snow somewhere on the southern hemisphere. In a fraction of the material, a thin diffuse cloud of gas and submicron particles spreads out in all directions, creating the tenuous exosphere of Enceladus, a not-quite atmosphere of water vapor and nitrogen and trace organic compounds that extends thousands of kilometers from the moon's surface. The Cassini spacecraft flew through this cloud on its first recognized detection of the plume in 2005. The instruments registered a spike in water vapor density as the spacecraft passed through the exosphere of Enceladus. The team analyzed the data, and they understood for the first time what Enceladus was doing. One instrument reading, one anomalous spike in water density, and the entire scientific understanding of Enceladus changed forever. You are at 100 kilometers altitude now. Enceladus is a sphere below you, small, white, perfect, like a marble in the dark. Saturn fills the background, enormous and cream-colored, the rings extending across your entire field of view. From here, you can see the E-ring. It is faint, far fainter than the main rings, but real, visible as a slight brightening in the space around Saturn's orbit, between roughly 3 and 8 Saturn radii. The E-ring is widest and brightest at the orbital distance of Enceladus, at exactly 4 Saturn radii from the planet's center. This was the original clue even before Cassini. Astronomers noted in the 1980s and 1990s that the E-ring was anomalously dense at Enceladus's orbit. Something was replenishing it. The ring has a lifetime. The ice particles that compose it are gradually removed by electromagnetic forces, by sublimation, by collisions, of only about 10,000 years. For the ring to exist at all, it must be continuously fed by something at Enceladus's orbital distance, by something erupting from Enceladus itself. The logic was there for decades before the instruments confirmed it. It just required the right spacecraft, at the right distance, with the right sensors, at the right moment. You look at the E-ring for a long time. You were thinking about the humans who built Cassini. The spacecraft was proposed in the early 1980s. It was approved for development in 1989. It was launched in October 1997 aboard a Titan 4B rocket from Cape Canaveral, Florida. It carried the mass of a small car, 2,150 kilograms, and it was packed with 12 distinct scientific instruments representing the contributions of 17 countries and hundreds of individual scientists and engineers. It traveled for nearly 7 years to reach Saturn. It executed an orbit insertion burn on July 1st, 2004, a 45-minute engine firing that had to work perfectly in a spacecraft operating beyond the reach of any real-time human intervention after 7 years in the vacuum of space. It worked. Cassini orbited Saturn for 13 years. It returned hundreds of gigabytes of scientific data. It made more than 400,000 images. It discovered 6 previously unknown moons of Saturn. It revealed the liquid methane lakes and rivers of Titan. It measured the winds in Saturn's atmosphere at speeds exceeding 1,800 kilometers per hour. And it discovered the plume of Enceladus. On September 15, 2017, Cassini ran out of propellant. The mission scientists had a choice. They could leave the spacecraft in orbit, but without propellant, they could not control it, and an uncontrolled Cassini might eventually impact Enceladus or Titan, potentially contaminating those worlds with terrestrial microorganisms that had survived the journey from Earth. So they chose the other option. They fired Cassini's thrusters one final time and directed it into Saturn's atmosphere. The spacecraft entered at a shallow angle and for the last time transmitted data, atmospheric composition readings from its deepest penetration into Saturn's clouds before the temperatures and pressures exceeded its structural limits, and it broke apart and became part of the planet it had spent 13 years studying. It is gone now, but everything it found is still here. You are watching the E-ring, the ring that Cassini confirmed was made of Enceladus, and you feel something that is not grief exactly but is adjacent to it. The loss of a machine. The recognition that the data it gathered will be analyzed for decades, that scientific papers based on Cassini data are still being published, will still be published for years to come, that the 13 years of observation have not yet been fully understood. A spacecraft is an extension of human curiosity. It goes where we cannot. It looks at things we cannot see. It measures what we cannot feel. And when it ends, something irreplaceable ends with it. Not the data persists. But the possibility of more data from that particular instrument, in that particular position, at that particular moment in the history of the Saturn system. That possibility closed on September 15th, 2017, over the clouds of Saturn, and Enceladus continued. The plume continued. The vents glowed. The ocean moved. And the scientists, back on Earth, kept reading. You begin your final descent toward the surface. Not toward the South Polar region this time. You want to see the rest of Enceladus before you go. You cross the terminator, the boundary between the illuminated and shadowed halves of the moon, and move into the night side. The night side of Enceladus is dark. Not completely dark. Saturn provides reflected light, and the rings provide reflected light, and together they illuminate the surface with a dim blue-gray glow. Saturn shine, the equivalent of Earth shine on our own moon. In this dim light, the surface has a different character. The brilliant whiteness of the day side is replaced by a softer, more ambiguous gray. The craters of the northern hemisphere, which you have not visited, are visible from above, shadowed differently in this light, their interiors dark and their rim walls faintly lit by the diffuse light from Saturn. You descend toward the northern hemisphere. The contrast with the south is immediate and dramatic. Where the south is smooth and young, the north is ancient and complex. The craters here range from simple bowl-shaped depressions a few kilometers across to multi-ring impact structures tens of kilometers in diameter. The largest impact features have central peaks, uplifts of ice caused by the rebound of the crater floor after impact, a feature that forms in large impacts in icy bodies throughout the outer solar system. Between the craters, the terrain is hummocky, irregular, with no clear pattern, the product of 4 billion years of small impacts, of slow tectonic deformation, of the gradual redistribution of ice under gravity and tidal stress. This is what the whole moon would look like if the South Pole were not anomalous. If whatever is happening at depth were not happening. If the ocean below were not warm enough, or the ice shell not thin enough, or the tidal heating not intense enough to drive the resurfacing that keeps the South young, the North is the default. The South is the exception. And the exception is everything. Without the South, Enceladus is just another small, cold, cratered moon. With the South, it is the most interesting world in the solar system. You sit down on the northern plain among the craters. From here, you cannot see the tiger stripes. You cannot see the plume, but you know they are there on the other side of this moon, 400 kilometers to your south. And you know what is below all of it. The same ocean. The global ocean covers the entire rocky core, north and south alike. Even here, in the ancient terrain of the northern hemisphere, there is an ocean below your feet. Farther below, the ice shell here is estimated to be 20 to 30 kilometers thick compared to 5 kilometers in the south, but present, liquid, moving. The ocean does not belong only to the South Pole. It belongs to the whole moon. The tiger stripes are just the place where the moon's interior reaches the surface, where the heat breaks through, where the water escapes. The rest of the ocean is private, sealed, unknown, an ocean larger than Earth's, and we have never directly touched it. We have only read its messages, carried upward through the ice by the forces that crack and recrack the southern shell, delivered to space in a plume of ice crystals and organic molecules and molecular hydrogen and all the other contents of a chemistry that has been running since before the first vertebrate drew breath on Earth. We have read those messages and understood what they say. And what they say is, come back. Come back with better instruments. Come back with a microscope. Come back with something that can look for cells. Come back and ask the question properly. You sit in the old terrain of the northern hemisphere and you look up at Saturn. From here, Saturn is slightly lower in the sky than it was from the South Pole. The geometry of the orbit places it at a different elevation depending on your latitude. The rings are tilted differently. The shadow of the planet falls differently across the disk. But it is the same planet, the same rings, the same light. You think about all the objects in this system, the 83 moons, the 4 ring groups, the magnetosphere, Saturn's magnetic field, extending millions of kilometers into space, trapping charged particles from the solar wind, interacting with the moons and rings in complex patterns that Cassini spent 13 years mapping. You think about the fact that every one of those moons is a world, a real place with a real surface and a real interior and a real history, and that among all of them, among every object in the Saturn system, one small white moon with 4 scratches on its south pole contains an ocean that might contain life. Might? the word that carries everything. You have been thinking in mights and maybes and possibles all week, and you are not frustrated by it. The uncertainty is the point. The uncertainty is what keeps the question alive. The moment the answer arrives, the moment an instrument on a future spacecraft resolves the question one way or another, this particular kind of wonder will end. Not wonder itself, but this specific, held-breath wonder of not knowing, of sitting on the surface of a moon that might be inhabited and not being able to tell, of looking at the plume and knowing it carries the chemistry of a seafloor you have visited, and understanding that the answer is in there, somewhere, if you could only read it finely enough. That wonder has a lifetime. And right now, in this moment in the history of science, you are inside it. You are in the window. This is what it feels like to live in the era of the question, before the answer, when everything is still possible. You stand. You take one last look around, the cratered northern plain, the gray-white ice stretching to the horizon, Saturn overhead, the faint arc of the E-ring visible in the sky as a slight brightening at Enceladus's orbital distance. You begin your ascent. Rising from the surface, the moon shrinks below you. The northern craters become features, then dots, then a texture on the surface of a shrinking sphere. The tiger stripes come into view as you rise high enough to see the South Pole again, 4 dark lines against the white glowing faintly in infrared, the plume rising from them in a coherent column that breaks apart into the diffuse cloud of the exosphere at higher altitudes. You watch the plume for a while as you ascend. It will be the last thing you see of Enceladus before the distance takes it from you. The plume that contains, possibly, the answer to one of the oldest questions in science. The plume that was quietly erupting here in the dark of the outer solar system for millions of years before anyone knew it existed. The plume that a spacecraft detected for the first time in 2005, not because anyone was looking for it, but because Cassini was simply doing its job, flying past a moon that wasn't supposed to be interesting, running its instruments because that is what you do, and noticing something that changed everything. Science works like that. Not always dramatically. Not always with a eureka moment. Sometimes it is a spike on a graph, a density reading that is slightly higher than expected, a mass spectrometer detecting something that isn't supposed to be there, a mission scientist looking at a number and saying, "Wait, wait, look at this. Look at what this moon is doing. You are very high now. Enceladus is a white point below you. Saturn fills the view ahead. You will travel back the way you came, back through the Saturn system, back through the outer solar system, back through the years of distance between here and Earth. The sun will grow larger as you travel inward. The temperature will rise. The density of the interplanetary medium will increase. And you will carry all of this with you. The tiger stripes, the plume, the hydrothermal vents, the ocean, the question. You carry all of it. The distance between you and Enceladus is increasing at 30 kilometers per second. By the time you sleep tonight, truly sleep deeply and completely, Enceladus will be millions of kilometers behind you. But it does not feel like leaving. It feels like carrying. You carry the memory of the blue fracture walls, the heat signature of Damascus sulcus on your instruments, the sight of the plume from altitude, the dozens of individual jets resolving into a single coherent fountain, the glow of the vent on the seafloor, orange-yellow in the cold and dark, surrounded by a mineral landscape that looks nothing like life and may be full of it. You carry the weight of the question, and the question is not a burden. It is a gift. The universe has given us a place where the answer might exist, and instruments capable of beginning to read it, and minds able to understand what the instruments say, and enough curiosity to keep sending things into the dark. That is not nothing. That is extraordinary. We are a species that built a spacecraft, packed it with instruments, sent it over 1 billion kilometers from home, and listened to what a moon had to say. The stars are all around you now. The sun is behind you, smaller than it was, but still the brightest object in the sky. Ahead, in the direction of travel, the stars are exactly where they have always been, unchanged by your journey, indifferent to your passage, burning at their own temperatures and their own distances, and on their own timescales that dwarf even the deep time of Enceladus. You are a long way from home, and home is a long way from the answer. But the distance between question and answer is getting shorter. Every year, every paper published, every instrument calibrated, every mission proposed and studied and funded and built and launched, the distance is getting shorter. You are heading home now, but the ocean you are leaving behind, the ocean that has never seen sunlight, that has been moving in the dark across geological time, so deep it dwarfs every human calendar, that may or may not contain something that metabolizes and reproduces and responds to its environment. That ocean will be here when we come back. It will still be here. It has been here longer than you can hold in mind. Give it a little more time, and let yourself rest now. You have traveled far. You have gone deeper than most people imagine is possible. You have floated in the ocean of another world and watched a hydrothermal vent glow in the dark and stood at the edge of a fracture that connects the surface of an ice moon to a sea that may be inhabited. You have done a remarkable thing tonight. And now it is time to come home. Not all the way. Just to the place between waking and sleep, where distances collapse and the weight of questions becomes the weight of a blanket. The stars are out there, exactly where they have always been. The dark is here. The ocean of Enceladus continues below its ice, as it has always continued, warm and full of chemistry that may or may not have learned, somewhere in its long history, to call itself alive. Let the plume rise. Let the E-ring drift. Let Saturn's rings catch the light of a sun that is, from here, just another star. And let yourself drift too. Gently, without direction. The way particles drift in the plume, released from the surface of a small world, following the physics of the moment, carried by forces larger than themselves, into a space that is unimaginably vast and perhaps not as empty as it looks. Good night. The ocean is still there. The question is still open. And that is the most beautiful thing in the solar system. If this story found you tonight, we would love for you to subscribe to Quiet Science at Bedtime And if you leave a like or hit the notification bell, it means the universe knows to send you the next one. Sleep well